All right, carrying on in the same topic, we're going to learn more about Calabi metrics machine learning from Magdalena Larfors from Uppsala.
Thank you very much. So first, let me join the other speakers in thanking the organizers for organizing this lovely school. I'm learning a lot, and it's been very enjoyable so far. Also, a great dinner yesterday. Thank you. Can you hear me all right? No. Possibly because I have not turned on the mic. Is that better? Can you hear me? Not sure. Yeah. The mic is working. Is that better? Very good. Okay, so I will try to pick up from where James finished and talk about how we can develop these numerical methods that we've heard about a bit further and use machine learning to learn about Calabi metrics. So the plan for this lecture is that we will talk about what we want to learn, so the Ritchie-Flat metric, and how we will do that efficiently. And what I wanted to do is to give some sort of overview of what has been done in our community regarding these questions in the past couple of years, without going into too much detail. So sort of try to give some sort of overarching description of the techniques that have been used and the different choices that different people have made. And then we will go into more details tomorrow. So that is the plan, and we'll see how it goes. Might just turn into complete confusion. If so, stop me and ask questions. What we know from Larry's and James' lectures is that we have these Calabi manifolds. They're compact, complex, and scalar. They admit this unique Ritchie-Flat metric for fixed scalar and complex structures. There are also these large databases of example manifolds that Lara mentioned. So we do have a nice playground where we can test our methods. We want to compute this Ritchie-Flat metric, and it requires solving a partial differential equation on a compact curved space. And we've heard about how that is highly non-trivial. So as I just said, the aim of these lectures is to show how we can use machine learning in this endeavor. And my goal, so when you're a teacher, you think about learning goals when you're delivering lectures. So is that you will know which packages exist and what they are designed to do, and also develop some familiarity with these methods and packages so that you can, if you have a physics problem where you would need a Calabi metric, you would be able to start using the packages. And then, of course, you will need to add on the stuff that you're interested in to them. But still, that's sort of the goal. So today, I'll do a bit of introduction to these machine learning implementations. What do they look like? And just review the 3 packages that I know of are available as open source code. Then I'll talk a bit more about the point sampling, basically picking up from where James left. Then I will talk about how we encode this in more detail, so the training and the loss functions, the accuracy and the error measures, and then I will give some examples. Tomorrow we'll do details. In the tutorials, there will be implementations and experiments. When I spoke to Yidi, we decided that maybe we will not do as much on Hedrick's code, so we will focus more on the machine learning bit. Yidi has one local, very hands-on exercise where you'll see really all of the code, and then there are some exercises with using these different packages with a focus on one called CY metric. And hopefully that will be useful. So that is the plan. I should also say that there are papers on this, of course. The main reference I will use are listed here on this slide. There are other papers that are not mentioned, and it's not because they're not interesting, but these are the ones that are most related to the packages that we will be talking about. Okay, so we've heard about the traditional methods. There's the Donaldson algorithm, which we haven't really seen, but just to say something about what it is, it's this fixed point scheme. You have this T operator that you iterate to find what is known as the balance metric, and the balance metric, which we will come back to, is something you can use to compute the Kähler potential that you're interested in. Then it's the functional minimization, which we've heard a lot about in James's very nice lecture. And what these traditional methods give you is some numerical approximation for the Kähler potential using a particular basis of function. And I will call that spectral basis. That goes under different names. James denoted these as these polynomials pk a or pk I. So in the machine learning methods, just to start zooming in on them, what you do is that you could either take these traditional methods and use machine learning to replace bits and pieces of them. And then naturally you will get the Kähler potential, and you will also have some of the benefits of these traditional methods. So for example, if you do this for the Donaldson algorithm, you can rely on the fact that Donaldson has this theorem saying that you will get the true Ritchie-Flat metric as you go to k into infinity. So that's maybe something that you would like to have. Otherwise, you can do this direct learning of the metric as, or you can apply machine learning directly without any reference to these traditional methods, and then you can learn either the Kähler potential or the Calabi-Yau metric directly. So these are the different choices you can make, and naturally this will give different kinds of architectures to your machine learning packages that you build, or the way that you structure your solution to this problem will look differently depending on what kind of methods you're using. Once you've done that and you want to check whether you actually have a Ritchie-Flat metric, then you will need some accuracy checks, and they are the same for all methods. So I will talk about them like in a global way. So to speak a bit for why you would want to be doing this, there are these benefits of the machine learning approach. So we have, it has been shown by the work of different people that you get this significant improvement in speed, performance, and scope. I will not show you any numbers on this. You will just have to take my word for it, but you will also experience, at least in the tutorial, how fast some of these methods are. And I will also maybe do a demo tomorrow where I'll show a bit of that. Also, there is this, so there's a scaling problem with these traditional methods. So this need for symmetry. So the fact that we have this basis that we expand everything in that blows up, and we need to restrict that, that's a problem, and you don't have it for machine learning. We can use it to, because we don't have that scaling problem, we can also attack more advanced Calabi-Yaus, more complicated Calabi-Yaus, which may be of more interest for the applications you're interested in. And there, we will talk a bit more about that tomorrow, and then we can also try to learn modular dependence. So we've heard a bit about that already from James, also the generalizations that we can hope to do. But another thing that we haven't really heard about yet is that there are these machine learning libraries that we can use. So as Fabian said in his lectures, if there are methods available for the problems that we're interested in, then we should try to use that. So in particular, there are these machine learning libraries like PyTorch, TensorFlow's JAX, that allows to efficiently compute derivatives and optimize loss functions. And as you will see today, and as you might already have understood from what you've heard from James and Lara, this is basically what we need to do. So we need to be able to, if you think about this functional approach, it's functional, we want to find the minimum of a functional. That's some sort of minimization problem, and the machine learning problems will be similar to that. So the fact that we have a good way of doing that using standard machine learning tools is great. Okay, so let's just remind ourselves what the problem is. We want to find the Ritchie-Flat metric, which means that we want to solve this Monge-Ampere equation. And that relates these two volume forms. So we have the Kähler form for the Calabi-Yau, that is the thing that we're after, JCY. So I'm really sorry, my notation will be completely different from the one that James used. I tried to think about this ahead, but it's very, some things you just do differently. I will try to comment on it. So anyway, omega is called the same thing. So omega is the holomorphic top form. It's this 3,0 form on the Calabi-Yau. And it gives us this Calabi-Yau volume form, which I will call G-vol Calabi-Yau. And the kappa here is some some constant. So omega is something that is known. The Calabiao-Kähler form, which gives us the Ritchie flat metric, G is Calabiao. So J Calabiao is the thing that we're after. This is unknown, but we do know other forms. So, for example, we have the Fubini-Studi Kähler form that we can we have sort of for free in all the constructions that we will talk about when it comes to Calabiao manifolds, and we can use that in order to solve this or to write down a way of solving this Marshall-Parr equation by finding the form that we're after in the same Kähler class as the Fubini-Studi Kähler form. So by adding this exact piece del bar phi, where phi is a function. So what we will do is to train a neural network that will predict this Calabiao metric that we're after, so the Ritchie flat. And if we talk about a particular example, so in this lecture, I will focus completely on the quinti because that's the manifold that most people have been working on. Then what we do, the way to see how we can compute these things is that we can go to a particular patch. So I will use x for the homogeneous coordinates of the ambient space. So on P4, we have x0 to x4 being the homogeneous coordinates. And then we have affine coordinates, which I will call z. So that's a change of notation compared to James. And we can write down a way of computing omega, which I think was mentioned in Larry's lectures. And that's that you can compute it using sort of a recipe formula. And this is, of course, something that you do then patch by patch. Similarly, for the Fubini-Studi metric, we have its explicit form here. So what we want to do then is to find a Kähler form, which is globally defined and which solves this Marshall-Parr equation. So how do we do that if we want to put this into a machine? Well, the first thing we need to do is that we need to take what we know about the Calabiao manifold and give that data to the computer. So what we will want to feed in are the things in yellow, so the moduli and some points on the Calabiao. Then we will devise some sort of machine learning package, some sort of machine learning model, which involves a neural net, where we will solve this equation using some sort of training algorithm. And this training algorithm will minimize a loss. So it will be very similar to the supervised learning that we heard Fabian talked about in the first lecture. In fact, one can say that it is supervised learning. What is different is that we do not know what the Calabiao metric is, so what the Ritchie flat metric is on the Calabiao. So we will have to be a bit clever when we define these loss functions. So this is where we encode the mathematics of this. Yeah. Then the network will give us a metric prediction. So in some sense, the network is the metric. And once we have it, we can compute the metric in other points on the manifold. We can test it, and we can compute error measures, and we can see whether this is Ritchie flat and to what degree it is Ritchie. So this is what a Calabiao metric package should do then. So it should implement this template, and it should do so in a way that that gives the this metric prediction. But the exact way of how you actually do this green part differs a bit between the different packages. Okay, so I've been mentioning packages a lot. So let me just say what they are and where you can find them. So there are 3 packages that I'm aware of on GitHub. I have worked with CUI metric, which has been written by Fabian Ruhle is here, and Robin Schneider was my PhD student. So my part of this work has been to do some physics with this and also to ask questions about how this package works. So I'm not one of the authors, but I'm quite familiar with the package. Then there's a package that Yidi and Mike Douglas have been constructing, which I don't think has a snappy name. So it's known as the holomorphic and bihomogeneous networks. The other 2 packages are called CY metric and CY JAX, so it's a bit shorter to write. But this is also available, and it's very nice. And then there's a 3rd package called CY JAX, It's written by Sven Krippendorf and Matthias Gerbes, and which you can also find on GitHub with the links given here. So thing to say about these packages, we will talk a bit more about them and what they do. They are open source and they can be freely used, and you can also contribute to them. So if you think that this is interesting, there are certainly ways of improving these packages, and there's certainly a way of contributing to this field by adding bits and pieces to these packages. Also, they use, as I've written here, they're using different, when it comes to these machine learning libraries, the choices are a bit different. So two of them are using TensorFlow. One is using Mathematica, also has a Mathematica version, and the third one is using JAX. Okay, so let's talk a bit about what it is that we feed into the machine learning algorithm. So this is not something that has anything to do with machine learning, really, but it's something that is very important. And we've just heard what James has been saying about this thing, so I can be a bit fast. However, first I should say something about notation confusion. So what James called here mass for the points that are in our sample, I will call weights, because that's another term that is used in the literature. Now, I will talk about weights here for the point sample, and then we will talk about neural networks, and there are weights there as well. So this kind of confusion is very common when you're doing something that is a bit interdisciplinary. So what is a model in machine learning is not the same as what is a model in physics. What's weights in one part of this story is not weights in another part of the story. So I just wanted to flag this, that this is a source of confusion, and one should be a bit mindful about what kind of words used. I should really have used mass, that would have been better. Anyway, so what do we want? We want a random point sample so that we can compute integrals. And these integrals are needed to check accuracy, as we will see in a bit down the line in this lecture. So, and numerically, what we'll do is that we want to evaluate these integrals using a weighted sum, as we heard in James' talks. So the overall factors here can look a bit confusing, but it depends a bit on how you define these measures that James called mu and mu prime. So we will need to get this random set of points, and there are various ways that one could imagine doing that. And we've already heard a bit about that, so I will be a bit brief. This is the method that James described, where you pick two uniformly sampled points on your ambient space, and then you create a line between them and intersect with the Calabi-Yau. And this is the standard way of sampling point, because it gives, in a good way, because it gives you points that are distributed with respect to the Fubini-Student metric, or with respect to the Fubini-Student measure. So this is the thing that we will use. And what I've described here is for the quintic, and one can generalize this for other kinds of ambient spaces, and I will say something more about that tomorrow. But what I wanted to say here is that there is a nice method that one can use. It's very quick, it's very cheap, and the reason for that is that we're basically sampling points on spheres, and there are these ready-made methods for sampling points on spheres. So that's also nice. You can sort of get a cheap way of getting your points from using methods that are standard. Okay, so once we have our sample, then these are sampled on the ambient space. They will be given in the homogeneous coordinates of the ambient space. If I have the quintic, these are these 5 coordinates x0 to x4 that are related by this rescaling. So in order to work with this on our manifold, or when we're computing things for the Calabi-Yau metric, what we need to do is to go to a patch. We divide our ambient space into patches, and we define the affine coordinates, then 4 of them. And then because we are imposing the defining polynomial being 0, this gives us 3 linear independent coordinates on our Calabi-Yau, and then we can compute these forms omega, and so the 3-form omega and the 2-form j for this. And we can also compute the weights for the numerical integration. So you will in your package for computing Calabi-Yau metrics, you will need to include some sort of point generator that does this for you, and this is provided in the package. Okay, so say then we have this set of points. We have sampled the points. We have the weights for every point. We have computed these various things. So we have this constant kappa because we can just compute it somewhere, and then it will be the same throughout space. It's constant, and we then have a way of giving points to some machine learning or giving data to some machine learning method. So what will we do? Well, we will pick a neural network. And as we've heard already, this neural network will have different layers. We will have an input layer where we will feed in the things that we know about the Calabi-Yau, so the points and possibly the moduli, if we want to train it to be moduli dependent. Then there will be some hidden layers where which work exactly as we've heard in Fabian's lectures, for example. So they will be connected in different ways by these kinds of matrices that includes that have parameters, and these parameters are what we will train in order to get good prediction for the metric. Now, in the Calabi-Yau literature so far, most of the networks that have been used are fully connected and feed forward, and they're not very deep. So they have a few hidden layers. So this is very, very different from the kind of cutting edge machine learning networks that are used in for more sophisticated problems than finding a Calabi-Yau metric, like predicting the next song on Spotify. So. So it's kind of strange that it actually works with these simple networks, but maybe it's also hinting to something hidden underneath the problem, that they aren't as that there is something there that one can learn from the fact that the simple networks work. Okay, so then what we do, we have this network. We would want to train it, so we will do that by minimizing certain loss functions that I will tell you about in a minute. And after the training, we should then have a prediction for the Calabi-Yau metric. Okay, so then we have to choose what we want to predict. Should we predict the metric, the Calabi potential, or this age matrix, which was mentioned as the parameters of Hedrick's method, James' talk, and so that's something we should decide, and then we should think about what kind of how we actually deal with the training, and then what error measures we need. So that brings us to the training. Any questions so far? Everything's crystal clear. Very good. Okay, so we will. So what we do when we're training this, well, we have to define a loss function, and then we want to train so that we minimize this loss function. So this is just standard stochastic gradient descent with using the backpropagation technique. So it's something that we've all heard about before in the school. So we have some complicated function, and we want to find the minimum of that function. Now it's so why can we do this? Well, we have these libraries. We want to use the libraries, and this is what they're good at doing. So they can efficiently solve this problem for us. So what we need to do is to be clever and tell the libraries what are the things that they should solve. And this is just so here I just have a little recap of what it is that we do. So we have our neural network, which has these layers, where given an input, we're computing data at the next layer. And this includes these weights and biases, which is the linear transformation of the data from one layer to another. And then we have the activation functions, which give us the nonlinearities in the network. So what we'll do then is that we want to compute loss gradients at the points that we are feeding into the network, and then we want to move towards a smaller loss. So we want to update the parameters, so these weights and biases, so that we are going to smaller loss. And then we want to repeat that for many points and hopefully have a good prediction that works in every point. So as you remember from Fabian's lectures, we're using backpropagation. So it's basically computing the loss gradients using the chain rule. We're moving from the end to the start. We're doing this in order not to get stuck in local minima. We're using this, this trick of dividing our data sample into smaller batches and updating the parameters for runs over these batches. And this is just standard techniques, nothing that has to do with string theory, nothing that's very advanced, and nothing that you need to tinker too much with. So the thing that you do need to think about is what kind of loss functions you do use. So here we should encode the math constraints that we want to solve. So we want to get this Ritchie flat metric, and we know that in order to get the Ritchie flat metric, well, the Ritchie tensor should vanish. So that's one thing. And then the Monge-Ampere equation is something that has been proven to be equivalent to that. So in a supervised setting, of course, what we would do is that we would have our input data, which would be the points on the Calabi-Yau, and then we would have an output data, which would be the metric then, and then we could compare after having the prediction whether we are close to the metric or not. So here we do not have that. So instead, what we're using is something that is called semi-supervised learning. So we're encoding these constraints that we want the metric to satisfy into loss functions. So for example, here is the most common loss function that is used, which is the Monge-Ampere loss function. It's quite similar to the one of the functionals that James wrote down, but it doesn't have any integration here. So what we have here is just a function that computes the difference between the metric or so the volume form that the predicted metric is giving you. So the thing that the neural network predicts, and compares that to omega wedge omega bar, which is this volume form that we know or knew in James's lecture. So if we have the Calabi-Yau metric, then this loss function should be 0, right? Because then these two volume forms should be the same. So what we're doing is that we're checking this condition point by point in our Calabi-Yau. And then we can, you see here that there are some bars and there's an n here, so we can compute this. We can either take the absolute value square of this, or we can take just the absolute value. Or so this is something you can play around a bit with. But the idea is that to try to enforce in each point that these two volume forms are the same. Okay. So that's a very natural thing to do. And it's also pretty cheap because you have, so the output of your neural network will give you either the Kähler potential or the prediction for the Calabi-Yau metric directly. So once you have that, then you just need to compute a determinant, no derivatives, anything. And then you just compare these two things. And this omega wedge omega bar computed in the point is something we have already from the point sample. This is very simple. Okay, so this is one thing we can compute. The other thing is to say, okay, we want to have the Ritchie tensor to be 0 as well. And as James was saying, one thing we can do in order to ensure that is to minimize the Ritchie scalar. So we had this Ritchie scalar functional. So we could try to do the similar thing here to say that, okay, we want the Ritchie scalar to be vanishing at every point as well. And then that will give us, as long if we're using these scalar identities, it will give us this kind of loss function here. And here you see, so here in this loss function, we have two derivatives. So we will need to compute that, and those are derivatives with respect to the input. Now, this is not something that you normally compute in using machine learning, but you can actually use the gradient computation techniques that these machine learning libraries include for computing, that are used in the backpropagation algorithm, for example. You can use those same techniques to compute derivatives with respect to the input. And then you can compute a loss function like this. And this is something that's also has been used to train a neural network. But however, you do need to compute these derivatives, and of course that's something that has a cost associated to it. Okay. So this is fine as long as you're say you're predicting the Kähler potential, and you're doing this on the quintic. So which gives some simplifications that I'll come more to tomorrow. But basically, what this buys you is that it guarantees that you stay in the Kähler setting all the time. Then this is fine. Either of these are fine. In particular, it's fine to compute the Ricci scalar in this way because you know that you will stay within the set of Kähler metrics all the time. But if you're allowing yourself some more freedom and you're letting your network loose and say that, okay, just go and predict the metric for me, then that's not necessarily guaranteed to be Kähler. So then you should be a bit cautious when it comes to any kind of loss function that is using information about the manifold being Kähler in the computation. Okay, so if we are doing that, then if we're predicting the metric rather than the Kähler potential, then we would actually have to check some further things. So we will need to check that the metric is a globally well-defined metric, so that it, as we look at overlaps of these patches that we have on our manifold, that these the metric that we have in one patch and the metric in another patch, that they agree. So that requires checking transition functions. So you have to encode this in a loss function. By the way, I should say that the way that these loss functions are written here, they are so these are the loss functions that are included in the CY metric package, and they are also described. All of the four that I'm talking about here are described in the paper by Lara and James and Fabian and other collaborators from 2020. So one of the references that I listed in the first slide. Okay, if we're computing, predicting the metric, then we also need to check that we need to enforce that we stay with a Kähler metric in order to get the Calabi-Yau metric. And also, if we're going beyond the quintic, which is something I'll talk about more tomorrow, if we have more Kähler parameters, then a problem can be that we are minimizing our metric by going outside of the Kähler class where we started, and then we're not solving the problem that we think we're solving. So that's something that we will talk a bit more tomorrow. But that's never going to be an issue on the quintic because the quintic only has one Kähler modulus, and therefore there is only the only thing that can happen is that we get a rescaling of the manifold, and that's something that we can take care of. So that's for the quintic, we don't really need that kind of loss function. Okay, so what I wanted to make clear from this is that the architectural choices, so in particular the choice of what we want to predict, is it the Kähler function, is it the Kähler potential, or is it the metric? This will lead to different requirements for what kind of loss functions we need. But you can basically do whatever you want as long as you put in a loss function that encodes the conditions that you want your prediction to satisfy. Right. Okay, so now I talked a bit about very broad brushstrokes how we design the network. I've talked about the loss functions. So the last global piece of information is how we check accuracy and performance of our networks. And then we can get into more details about the different packages. So one thing we do is that, as in is always part of the standard machine learning way of working, is that you train your network on a particular set of points, and then you test it on some separate set of points, so that you check that you haven't just fitted your parameters to the small quirky fluctuations of the data set that you had, but it's actually something that is capturing more interesting features of the system. So our inputs then is that we train it with these the points on the Calabi-Yau, and we want to measure the performance. So the performance then in our case is this Ritchie-Flat metric. So we want to check if the Monge-Ampere equation holds and if the metric is Ritchie-Flat. And there are established benchmarks for this, developed for these other numerical methods. So it's good to stay with the same kind of measures. So one is known as the sigma measure, and it's basically just checking whether whether the Monge-Ampere equation holds, and in particular whether these two volume forms are the same, and then taking the integral of that. So this is exactly the Monge-Ampere functional that James had. And then we have the analog of the Ritchie functional, which is then checking that the Ritchie scalar, when integrated over the Calabi-Yau, is small. So we will, and we compute these. So once you have your network, you can compute these things in all the points of your test set, and then you evaluate these integrals using this numeric computation as a weighted sum. Okay. So, those are the generalities. So now we can look a bit more into what people actually have done. So the neural nets, as I already said, we have these different layers. We're training it using the standard routines, and then we're checking it with these different measures at the end. So in these three different implementations, they basically correspond to three different choices for what you want to learn. So in CY-JAX, the focus is to learn on learning the Kähler potential, and also in learning this balance metric H. So the metric, I shouldn't point there, the Hermitian matrix H that goes into constructing the Kähler potential using the spectral basis. Yes.
So are they just using the algebraic ansatz and then getting the thing closest to Ritchie-Flat, or are they learning the balance metric?
So I think they have, you can do both in the package, if I understand it correctly. I should say that I don't know this well enough to be able to answer, because I haven't used the package much myself. But from the things, from the things I've heard and read about it, this is what I understand, so that you can do both. So either learn H or learn K. So H emission matrix or the Kähler potential. So but the spectral basis, I understand, is an important part of this package. It's part of and the motivation for using that is something that we can discuss. Then there's the package by Yidi and Mike, where they learn the Kähler potential directly. And then there is CY metric, where you learn the metric directly. So those are the three packages, and how they differ in choices for implementations. So what are the pros and cons of these different ways of learning things? Well, if you learn the emission matrix H or K, then you're guaranteed to get a Kähler prediction. You're guaranteed to get something that is globally defined. And if you're using some Donaldson algorithm in some way, then you have this guarantee that your metric will converge to the Ritchie-Flat metric as K goes to infinity. Of course, that's never a limit that you can take practically, but still it can be something that you're interested in. However, if you're using a spectral basis when doing this, then you have a scaling problem. And there is no generalization beyond Kähler if you're doing this. So the pros and cons then of learning the metric is that's basically the reverse of that. So, well, you're always learning 9 components of a 3x3 emission metric. So that's not scaling in any way. You have the same number of outputs always. It generalizes beyond the Kähler setting. But you need to enforce that the metric is Kähler and that it is globally defined in your training. So this is something that in principle is not necessarily going to hold. And I will come back a bit to that tomorrow when that can be important. So it depends a bit on what you want to do, what you should choose. Okay, so now I've sort of said described how these packages, what they do. And I wanted to go in a bit more into detail and talk about some various experiments that have been done. And I have about 10 minutes, so that should be enough for that. So these are things that I've just picked from the literature so far. So different papers. And of course, and this is sort of, so in these papers, they're doing more things. So I've picked particular examples that I think are illustrating interesting ways of how you can apply these kind of methods. And it's not supposed to be covering or just showing everything that one can do. There's certainly more that you can learn about in tomorrow's lectures and also in these papers. So the first thing I want to say something about is this strategy to learn Donaldson's emission matrix H. So the idea here is that you have, as shown here on this picture, which comes from Lara and James's and Fabian's and Sven's and all others paper from 2020. So the idea here is that you take as input to your neural model the parameter psi here, which is the complex structure modulus for a particular version of the quintic. And then you train a neural network that predicts this matrix H for you, and then you use that to compute your Calabi-Yau metric. So in a bit more detail, how does this work? Well, in Donaldson's algorithm, what you have is that you compute your Kähler potential in the way that James has shown in his last lecture. So this is something that should look familiar. You have this basis of polynomials, which are here called S instead of P. But you have a basis of polynomials, and then you have this emission matrix H, which are the parameters that you want to learn in the, not machine learning parameters, but the parameters in the way that James talked about them. And then you want to compute the Kähler potential using this expansion. So that, of course, requires that you know what this basis is. So you need to provide that. And this is something that you can compute to a particular order of k in the sample points that you have. So these are just polynomials of your coordinates. So you have the coordinates of the points, and you just compute the polynomials. So this is something that you compute and you store. And then what Donaldson's algorithm is doing is that it gives you a numerical scheme for how to iteratively compute better and better approximations or better versions of this emission matrix H until you get to what is known as the balanced metric or balanced emission matrix. And this is a fixed point of this iterative scheme. So once you don't go any further, then you know that you've gotten to the right matrix, and this takes about 10 iterations, so it converges pretty fast. So of course, there are problems with these methods that James has already talked about, so we can skip that. But so the idea then with doing this with machine learning again, as far as I understand, is that you can, instead of using this fixed point scheme, you can take a neural network that predicts age instead. This has some advantages. So first, one advantage is that you then get, so you can train this network at different points for the complex structure moduli. And as James mentioned, this is one of the problems with Donaldson's method, is that you have to do this at fixed points in moduli space. So here you train your network at different points in moduli space, and you can then get moduli dependent matrix H, which is certainly a big advantage. And another fun thing about this is that this is actually something where you can apply supervised learning. So this is a way where you can test whether it's actually feasible to try to do these things. So this is also one of the earliest, a reason why this was tried very early, that you can do this in a supervised way, because you can use Donaldson and compute what age is, and then train your network using that, and then compare in the standard way with some mean square error, for example, as a loss function. So it's interesting to see that there are situations where you can apply this completely standard supervised learning also in the problem of machine learning Calabi-Yau metrics. Of course, that if you do that, then you have all the cost of computing age with the Donaldson algorithm when you're training your network, so you don't gain a lot by doing that, but it's good in principle to be able to see that can be done. You can also do this in the semi-supervised setting. So you use either the Monge-Ampere loss function that we've seen, or the Ritchie loss function, and then you train and you get your emission matrix. So here are some experiments that were reported in this paper. So for this particular quintic, the dwarf quintic with one complex structure modulus, for k equals to 3, so there's a 35-dimensional basis of sections, and with this particular choices that you input. So neural networks likes real things, so you don't want to input a complex structure modulus. It's a complex number. So they chose to divide it into a real and imaginary part, and also the absolute value. And then they, in this particular experiment, the output was the real and imaginary components of this emission matrix. So what we see here is then the table shows the structure, how the neural network was set up, so the number of nodes in the different layers, what kind of activation functions were used, and also the number of parameters that were needed for this. And then we see a comparison here on the right between so for different values of psi here, there's different random sampled points in a particular range of psi. We can see how these different methods perform. So you can see that for some of these points, the Donaldson algorithm is performing better. So the Donaldson is in blue, and the neural network prediction is in orange, and the Donaldson algorithm is performing better. So a lower value of sigma, which is the loss function, than the neural network. But in other points, the neural network is predicting better. And this is showing exactly this point that James raised, that even though Donaldson has this k into going to infinity argument, that it is the best prediction, then for a finite value of k, it's not guaranteed to be the best prediction. Also, this is computed on the test set, so there was a comparison in green here with the nearest value in the training set for the sigma loss. Perhaps a bit unusual. Okay, so that's one experiment that has been done. And there are others. So one, you can learn the Kähler potential directly. An example of that is what is reported on in this paper by Douglas and Yidi and collaborators from the same year. So if you want to learn the Kähler potential directly, then what you want to do is to input in your neural network the points of the Calabi-Yau, possibly the complex structure modulus as well, if you do want to do this in a modular dependent way. And then as the output, you want to have your prediction from K. There is a slight problem here, is that just as for the Calabi-Yau metric, where we discussed a bit that if you predict the metric, you need to check that it's globally defined. In principle, you need to do the same also for the Kähler function. As for the Kähler potential. Now, this is a function, so it's slightly simpler. And it is guaranteed if you expand it in this section, in the spectral basis, or the basis of polynomial, or the basis of sections of line bundles of a particular type. So this is guaranteed in Donaldson's algorithm and in this functional approach. And this is also one of the reasons why you would want to use that kind of basis. What Yidi and collaborators did was to solve this problem of having something that is globally defined by including an extra embedding layer in the networks, basically. So you ensure that your network is satisfying the constraints of giving something that is globally defined from the get-go by either restricting it to be holomorphic or bihomogeneous. So bihomogeneous means that it's basically what's written here. So you take your points and instead of just feeding in the points, you make combinations which are of a particular degree in both the coordinates and the complex conjugate of the coordinates. So what is done in what is known as the bihomogeneous network, which is the experiment I will show next, is that you input in your network this combination of coordinates times complex conjugate of the coordinates, take the real and imaginary part of that in order to have real things in your network. And then you use as an activation function, not the sigmoid or the tanh or something like that, but you use something that also preserves the homogeneity, or that gives you something that has a given homogeneity. So the activation function that is chosen in these experiments is just the square. So you square your data as you go from one layer to the other, which is, well, obviously nonlinear, so that works. And it's also changing the homogeneous degree of your data inside your network in a very clear way. You know what's happening. And with that, you can check that the Kähler potential that you predict is indeed globally defined. So here is some plots for training of such networks. It's using semi-supervised learning. It's the Montchampère loss again, and this is a plot of the sigma measure on the training data that is shown here, for particular different choices of the network. So one can see here that you have a really, you have a nice and rather interesting development of the sigma loss over the training epochs, yeah, where it's going down and thus giving you better approximations. So I'm running a bit out of time, and we should try to get coffee at some point. So I will say here that a nice thing of these networks is that they're very efficient. They're fast. They allow for looking at non-symmetric quintics, so there's no need of restricting to these particular quintics where you have a lot of symmetry, because you're not using the spectral basis in the way that was done before. That's nice. However, you told me that you might have a problem with gradient blowups because you're squaring things. So maybe you cannot build a very deep network, but on the other hand, we've seen that we can do with rather shallow networks, and maybe that's not really an issue. Okay, the last thing I want to say before finishing today is that, of course, the third option should also be mentioned, so we can directly learn the metric using a neural network. Here you input the data, you output the metric. You can either choose, you can have some different answers for how you want your metric to look at. We'll look more at that tomorrow in detail. And then here, the only thing you can do, you cannot do supervised learning, you have to do semi-supervised learning. You have these custom loss functions, you need all of them in the general case. And here are the answers that you can choose. And here are some examples, a bit fuzzy, sorry. Not sure what happened there. But anyway, here are some examples on the Fermat Quintic for different kinds of metric ansatz, and using some particular choice for the metric for the network with a width of 64, and there are 3 layers. They're fully connected Gelu activation functions. And what can be seen here, if you squint your eyes a bit, because of the fuzziness, is that you see what these are showing are the loss functions, how they're going down over training. And similarly, in the bottom row, you see the sigma measure to the left and the Ritchie measure to the right on test data. I'll see if I can get these to work in a better way tomorrow. Okay, so to summarize this lecture then, what I wanted to tell you is, so I wanted to argue a bit, but I have basically just said it in words, that with machine learning, we can improve on other numerical methods for learning Calabi-Yau metrics. And the things that are improving are the speed, the performance, and the scope. There are different packages available, and that can be used. And the architecture of these packages differ because depending on your goals, you may want to learn different things. The loss functions are key, so that's really where the physics and the math comes into the problem, into these implementations. That's where you encode your knowledge about Kähler geometry, about Calabi-Yau geometry, and about the equations that needs to be satisfied. You use these standard machine learning libraries that allows you to efficiently train your network and to efficiently compute derivatives, and that's something that is key for these things to work and to be fast and reliable. And this, again, I'm showing this picture here. This is what you need. If you want to construct a machine learning algorithm of your own that will learn the metric on a Calabi-Yau, this is what you need. You'll need some way of generating points and feeding the moduli into your system. You need to build your machine learning model, include your loss functions, and then you need a way of checking your performance using error measures. And I'll stop there. Thank you.
Great. Questions for Magdalena?
Could you go back to slide 27 real quick? There was something that was a bit confusing to me.
This one?
27.
27.
Yes. Right. You say there that you should be able to turn them on and off, but wouldn't these be requirements you always want to be satisfied? So shouldn't you be checking, shouldn't you always have those loss functions switched on?
Yeah, you can, of course, you can have them. They will, so the thing is that if you're always learning a Kähler, I mean, if you know from the way that you've constructed the problem that you're learning the Kähler potential, then checking Kähler loss is not going to buy you anything. You know, you can use it in your training, but it will just be 0 all the time. So it will not really affect anything. So if you have it in your package, then it's no, you can include it or not. But in some packages, you might not even have it because they're geared towards learning the Kähler potential, and then you wouldn't even code it. Maybe that's a better way of saying it.
Right. Thanks.
Could you comment on the results of this paper from the perspective of like string theory computations? Like, are we sufficiently numerically accurate that we can start to put the metric into and do computations that we couldn't previously to some limited degree? Or are we still not precise enough, or how far away are we?
That's an excellent question. So the question is whether we are now at a stage where we have metrics that are accurate enough to compute things in string theory. And I would say not quite. We're not quite there yet. So there's certainly scope for work to be done. What has been done is that, for example, by Fabian, the computation of spectra for Laplacians using these metrics have been done. So that's something that we can do. Also, when it comes to heterotic model building and going towards solving the constraints that the gauge fields need to satisfy there's also work has been done and using these kind of approximate metrics. And that has been done already before with using these other tools for, like the Donaldson algorithm for computing that. I would say that there's still a lot to be done before this is practically useful, but we're taking steps towards it.
Thank you.
Yeah, Fabian has a comment. Yeah.
Just the numbers in the case where we could compute the errors are at the
That's of course also a very good question. So Fabian says that in the cases that it could compute, the errors were at the sub-percent level. And this is, what is the accuracy that we want is also something that is not quite known yet. So I would envision that there will be some bit of back and forth where you're trying the methods and then you see that, okay, maybe they weren't good enough, and then you go back to perfecting the methods.
I would agree with that. I would also say as well as no one has written down something on the board on complex structure. So it kind of just depends on how you
Exactly, and that's also so one of the reasons why I wanted to present it in this way is that I think that depending on what you want to do, you will be interested either in methods that are very general and then can cover lots of different cases, different kinds of Calabi-Yau's and so on, or you want to use something that is really tailor-made for the exact Calabi-Yau manifold that you're interested in at the exact location, or some small region of moduli space that for some reason is important for you. Maybe you have some flux stabilizing all the complex structure moduli and you're just left with a Kähler moduli and you want something to understand how things vary with respect to those. I mean, that's not there yet, but it may be something that one should try to develop.
Fabian?
Just a comment to what James said. So these percent level accuracies, so we check them for the spectrum computation, and we check them for the essentially for the Hermitian-Mills equation, and that was done on a random tetraquadric. So this was not at the generic point in modular space of a. That's what I mean. Yeah.
Just as one further physics comment, to do the types of, the big prize of like, let's work out this, low energy Lagrangian that I mentioned in the first lecture on the series, that moduli dependence is really key. And that's a big thing that, so there's been some groups that have made good progress towards that. But as James just pointed out, having full moduli dependence of the metric is still the way out. And that would be a great price if we could do it. Other questions? All right, if not, let's thank Magdalena again. Break for coffee. And